The biophysical chemistry we are going to discuss from today onwards. And before understanding the biophysical chemistry, you should be thoroughly knowing the concepts of acids and bases. What is an acid and what is a base? This fundamental idea has to be clearly understood. You please have a separate notebook for biophysical chemistry and try to note down things. Even a small composition note book will be sufficient. You note down all the important points what I am telling you. I'm not going to write anything today, or I'm not going to show you any PowerPoint projections today. Just I'm going to speak, and I want all of you to take down what I'm discussing. So in olden days, when the scientific inventions were not that much familiar, people believed acid is the substance which has a sharp and a piercing taste. Suppose you are taking a substance and put it on your tongue and you experience some piercing taste or some sharp taste, something like a lemon put on your tongue. Any substance which gives such a taste was called an acid. This was the first idea. Because a lemon or any other citrus fruits, even tomato, when you put it on the tongue, you are getting a sharp and a piercing taste. That was the old idea of acids. And later on, Lavoisier, another great man, who gave the idea acidity of a substance is due to the presence of oxygen. A substance becomes acidic when it has oxygen as one of its components. This was the idea given by Lavoisier. Later on, another question was arisen by Humphrey and Davy. He asked, hydrochloric acid is an acid, but it does not contain oxygen. So there are acids even without oxygen. So we cannot generalize that the substances which have oxygen will act as an acid. There are acids without oxygen. You know, the very fundamental acid-base theory or the theory of electrolytic substances was given by Arrhenius. But the Arrhenius PhD dissertation was given the passing minimum mark in those days. Arrhenius' idea. According to his idea, he only gave the idea of electrolytic dissociation in water. When you put an electrolytic substance in water, the electrolytic substance will undergo dissociation to form anions and cations. See, we can do a very small qualitative analysis. Suppose you are taking a solution, you are trying to conduct electricity through the solution, and you are trying to light an electric bulb. If the bulb glows bright, then the solution has plenty of ions, which means the substance dissolved in the water is a strong electrolyte. If a weak electrolyte is present in the water, then the bulb will glow dull. There will be only a dull glowing in the bulb. Therefore, you can understand whether it is a strong acid or a weak acid on the basis of how the bulb glows when the electricity is passed through the solution. So Arrhenius gave the theory of electrolytic dissociation. So what is an electrolyte? The electrolyte is the substance which readily gets dissolved in water. What is a non-electrolyte? Non-electrolyte will not get dissociated in aqueous solutions. But mainly water is a very poor conductor because water itself will not undergo self-ionization. Therefore, substances can be divided into two types. One is electrolytes and the other one is non-electrolytes. Electrolytes are the substances which dissociate in aqueous solutions. Non-electrolytes are the substances which do not dissociate in aqueous solutions. Even the electrolytes can be divided into two types. One is a strong electrolyte and the other one is the weak electrolyte. So strong electrolyte is the one which readily dissolves and which readily gets dissociated in aqueous solutions to give ions. Whereas weak electrolytes, they do not dissociate to a greater extent in an aqueous solutions. Say for example, sodium chloride is a strong electrolyte. Hydrochloric acid is a strong electrolyte. Sodium hydroxide is a strong electrolyte. Even acetic acid is a weak electrolyte. Ammonium chloride is a weak electrolyte. Ammonium hydroxide is a weak electrolyte. Now, normally all the salts, what is a salt? Salt is a combination of acid and a base. When an acid is combined with a base, what you are getting is a salt and water. So a salt, you can think of various combinations, a strong acid and a strong base, a strong acid and a weak base, a weak acid and a strong base, a weak acid and a weak base. So these combinations, whatever may be the combinations, the salt that is formed will always be a strong electrolyte. Maybe their nature be different. See, strong acid, strong base, the salt is a neutral acid. Suppose if you take a sodium hydroxide and acetic acid, you are getting sodium acetate. Sodium acetate is a strong electrolyte. If you take hydrochloric acid and ammonium hydroxide, hydrochloric acid is a strong acid. Ammonium hydroxide is a weak base, but your salt ammonium chloride is a strong electrolyte. You take acetic acid and ammonium hydroxide, both are weak, but ammonium acetate is a strong electrolyte which exists. But their alkaline nature and acidic nature will be different. Only when strong electrolyte and a strong acid and a strong base combine, you are getting a neutral salt. Otherwise, you will get an acidic salt or an alkaline salt, something like that. But their acidic nature and alkaline nature will change, but the strong nature and the weak nature, all the salts are found to be strong electrolytes. That means in aqueous solution, they all exist in ionic forms. So now you should understand very carefully, and later on another idea came. The substances which dissociate and give H plus ions are called acids, or I can say they are proton donors. Or the substances which dissolve and give out OH minus ions are bases. They are bases. So this was the next understanding came. So acids are H plus ion producers. Bases are OH minus ion producers. Now you write an equation. I just tell you, you write this equation, HNO3 giving H plus and NO3 minus. Very simple equation. This is the equation for the dissociation of nitric acid. HNO3 gives H plus and NO3 minus. This is an example for strong electrolyte. Even at higher concentrations, nitric acid exists in ionized form in aqueous solutions. Now you write another equation, HNO2, HNO2, nitrous acid, double side arrow, equilibrium arrow, H plus plus NO2 minus. This is a weak acid. This is a weak acid. Whereas nitric acid is a strong acid. The reason is why I am putting a double side arrow between HNO2 and H plus plus NO2 minus. The reason is the dissociation and the association, that is the forward reaction and the reverse reaction, they take place simultaneously in the case of weak electrolytes. You are taking a small beaker with water and you are adding acetic acid. The acetic acid is actually having a tendency to dissociate themselves. Therefore, what will happen? CH3COO minus and H plus will come out. CH3COO minus and H plus will come out. But their tendency to form the ions and their tendency to combine, they are almost equal, or the rate of reaction towards the dissociation and the rate of reaction towards the association, they are almost equal. Therefore, an equilibrium is existing between the dissociated molecules and the undissociated molecules. So this kind of thing is observed only in the case of weak electrolytes. Whereas strong electrolytes, they dissociate and the ions will get separated and the ions will go off. And these ions, they do not have the tendency to combine again. Therefore, even at higher concentrations, the strong electrolytes remain dissociated. So the dissociated ions are found even at higher concentrations. But for weak electrolytes, undissociated molecules are found even at higher dilutions. Even if you dilute to infinity, you are taking a very small quantity of the substance and you are adding a very large amount of the solvent and the dilution goes to a greater level. The dilution is infinity. Even then, a few molecules of acetic acid will remain undissociated. That is the difference between a strong electrolyte and a weak electrolyte. Therefore, in order to get into the biophysical chemistry, even before discussing the Anderson-Hasselbalch equation and the important ideas behind the conjugate acid and conjugate base, you have to understand the Arrhenius theory of strong electrolytes. So what Arrhenius said? Arrhenius said the substances are composed of ions of opposite charges. That is the first assumption. Second one, when they are put into aqueous substance or when you are put into an aqueous solvent, these electrolytes will get dissociated into ions. That is the second one. Third one, as the ions are of opposite charges, they are all tending to attract each other even in the solution, but they are free to move from one place to the other place. That is the other assumption. So these are all the basic assumptions made by Arrhenius. Now, so Arrhenius theory, point number one, in aqueous solutions, the strong electrolytes remain in ionized form. That is the point number one. The theory limits to the basis of hydroxide compounds only. That is the drawback of this theory. Arrhenius theory limits itself to the basis of hydroxides. It is not able to explain. Even ammonia solution is alkaline. But Arrhenius theory was not able to explain the alkaline nature of ammonia solution. So later on, another theory came. So far, whatever we have seen, what is a strong electrolyte, what is a weak electrolyte, and also we have seen what is Arrhenius theory and how the dissociation is complete in the case of strong electrolytes and how the dissociations are incomplete in the case of weak electrolytes, and all these things we have seen. Now we are getting into another theory called Bronsted and Lowry theory. Actually, I'm not going to discuss all these theories in detail because these details are only the backgrounds for the biophysical chemistry. Actually, they are not the core subject area. They are only the background. So we actually start the biophysical chemistry from buffer. So before going to the buffer, before going to discuss how the buffer is able to maintain its pH and all that, you have to understand what is pH and you have to understand what is acid, you have to understand what is basis. That is why these fundamental ideas are being discussed. Now, according to Bronsted and Lowry theory, acid is a proton donor. Acid is a proton donor and base is a proton acceptor. Acid is a proton donor and base is an acid acceptor. Just a minute, I request that. So, according to Bronsted theory, acid is a proton donor and base is a proton acceptor. And later on, another theory came, Lewis theory. According to Lewis theory, bases are electron donors and acids are electron acceptors. Acids are electron acceptors and the bases are electron donors. Actually, in this point, I want to discuss a little bit, go away from the subject, and I would like to discuss with you. You take ammonia. Ammonia is a base because it has a lone pair of electron to donate. So according to Lewis' concept, ammonia is a base which is able to donate a pair of electrons. If you take a boron trifluoride molecule, which has a vacant orbital where it can accommodate 2 electrons, that is why BF3 is called Lewis acid and NH3 is called Lewis base, and when BF3 and NH3 combine, they form an adduct where both the electrons from the ammonia are donated to BF3 molecule. Now, I want to ask you one question. What about ammonia with 1H replaced by CH3? Methylamine. If you take CH3NH2, you know CH3 is an electron donating group. So the nitrogen is having a lone pair of electron. Now the CH3 group is again pushing the electron density towards the nitrogen. Now the nitrogen becomes more electronegative, or the electron density is found to be more on the nitrogen now. Therefore, it is readily, it gives the lone pair of electron. Therefore, the basicity of methylamine is greater than the basicity of ammonia. You should understand this. You should understand this. Why methylamine is more basic than ammonia? Because the amino group which is present, in the methylamine is an electron donating group. Therefore, it pushes electron density towards the nitrogen, and the nitrogen becomes more electron rich. Therefore, the electrons are readily given. Now you compare dimethylamine. 2 methyl groups are present. What will happen? 2 methyl groups will donate the electrons. They will push the electron density. Now the lone pair will be much easily given. You think of another thing. 3 trimethylamine. all the nitrogens in the ammonia are replaced by amino groups. What will happen? Now all the methyl groups will push the electron density and the nitrogen will be very rich in electron. Therefore, much easily that will donate the electron. Therefore, if you want to arrange ammonia, methylamine, dimethylamine, and trimethylamine, all these things according to the order of their basicity. Ammonia is found to be the least basic. Methylamine is found to be more basic. Dimethylamine is found to be much more basic, and trimethylamine is having the highest basicity. So the basic nature increases like this. More alkaline, which is more alkaline, the trimethylamine, which is the least alkaline, is ammonia. So it is because of the inductive effect of the electron. Now my question is, this discussion is true only in the case of gaseous state. This is another important idea. Whatever we have discussed in the view of inductive effect holds good only in the case of liquid substances. Sorry, only in the case of gaseous substances. But if you go to liquid state, the trend is just the opposite. In liquid state, ammonia is highly alkaline, whereas trimethylamine is the least alkaline. The reason is, what happens in liquid state, their structure is stretched due to bulky nature. See, ammonia is pyramidal in shape. When this one bond is occupied by methyl group, it stretches out. When the other bond is also occupied by the methyl group, it stretches out. When other bond is also occupied by another methyl group, it stretches out. Therefore, that pyramidal structure slightly gets enlarged, and for trimethylamine, it almost becomes closely planar. Therefore, the lone pair that is sitting on the nitrogen is not available for reaction because it is almost found inside. Therefore, the trend is reversed in the solution state. So, my dear student friends, we are discussing both polarity in physical chemistry 1, biophysical chemistry in physical chemistry 2, and the symmetry in group theory. So everything is interlinked. You should not try to understand the subjects separately. They are all interlinked. So mere the nature or the strength of alkaline nature in gaseous state is entirely different from the strength of the alkaline nature in liquid state, because the symmetry also plays a vital role. Not only the inductive effect, but the symmetry also plays a vital role in determining the basic nature of the substances. Therefore, according to Lewis' concept, acid is an electron acceptor, whereas base is an electron donor. This is the fundamental idea you should have. So the difference between the Bronsted and Lowry theory and the Lewis theory are this. Bronsted and Lowry said acid is a proton donor, base is a proton acceptor. But Lewis said acid is an electron acceptor and base is an electron donor. So this is the difference between Bronsted and Lowry principle and the Lewis principle. Now look here, you take down a small reaction, you try to write this reaction by yourself so that you will understand. Sulfuric acid, H2SO4, an equilibrium sign, then H plus HSO4 minus. Have you taken down? H2SO4 equilibrium sign, H plus HSO4 minus. Now, you carefully look at the reaction. The H2SO4 is a proton donor. When you look at this equation from left to right, H2SO4 has lost a proton and HSO4 minus is formed. When you look at the reverse reaction, HSO4 minus is a proton acceptor, and after accepting the proton, it becomes H2SO4. So H2SO4 is an acid according to Bronsted theory because it is a proton donor. But on the left side, HSO4 minus is a proton acceptor. After accepting a proton, it becomes sulfuric acid. Therefore, I can say in the entire equation, H2SO4 is an acid and HSO4 minus is a base. Are you able to understand? So H2SO4 is an acid, HSO4 minus is a base. Similarly for HCl, H plus plus Cl minus. Now HCl is a proton donor, therefore it is an acid. But Cl minus is a proton acceptor, therefore it is a base. Now I call it a conjugate base. That is the idea. This pair is called a conjugate acid-base pair. So H2SO4 is acid and its conjugate base is HSO4 minus. HCl is an acid and its conjugate base is Cl minus. Now, if the conjugate base is strong, then the acid is weak. If the conjugate base is weak, then its acid is strong. Watch closely. Watch closely. Suppose I take H3O plus ion. H3O plus ion. H3O plus ion can become H plus and H2O. So this H3O plus ion is an acid because it is a proton donor. So its conjugate base is water. Water is its conjugate base. Suppose if I say an acid is strong, then its conjugate base will be weak. If I say a base is strong, then its conjugate acid will be weak. Say for example, I want to compare this. You take a hydrochloric acid, take a hydrochloric acid. It is, I disconnect the meeting and then rejoin.